Okay, good evening. My topic for tonight will be trigonometry, a long video format discussion. And this is now trigonometry lesson number 5. Okay, let's proceed. This is a new topic. The lesson for tonight will be trigonometry lesson number 5. The title of the topic is example problem on angular speed. The problem is still related to angles. Okay, let's try to bring out an example problem. So, meaning to say, this is now an application of the concepts on our knowledge of angles. Okay, angles, that is in degrees, radians, and other things. Okay, let's try to bring out an example problem. The flywheel of an engine is rotating at 115 revolutions per minute. How fast is the point on the ring of the flywheel? So we are given the flywheel. Traveling if the diameter is 36 inches. Okay, flywheel is actually a set of a what you call this metal thing in which will rotate the what you call this the cylinders of an engine for the engine to operate the wheels. Or just to simplify the figure of the flywheel, we just bring out just a simple circular thing like this, and we call this a flywheel. The radius is 18 inches because the diameter is 36. Diameter is 36, so the radius will be 18 inches. Flywheel is the one that rotates the, what you call this, the differential thing on a truck or car, okay, for which that differential thing will rotate the back wheels, or if it is a front drive, okay, as the flywheel rotates, okay, the cylinders will go up and down, okay, as it goes up and down, okay, it will try to rotate the front wheels if it's a front wheel drive. Just to simplify the figure, we just will just draw a circle and we represent this as a flywheel. The radius is 18 inches because the diameter is 36. Radius is 1/2 of 36 plus 18. And Greek letter omega. Greek letter omega represents angular speed under the study of kinematics. So I place it here, omega is 115 RPM, meaning revolutions per minute. The problem is asking if we got a point here, a point on the rim of the flywheel, it's rotating at 150 revolutions per minute. If we try to bring out the speed of this in a straight line, what will be the speed? So actually this will now be a relation of an angular movement and a linear movement. Okay, so the concept of the problem here is what will be the relation of this angular rotation with respect to angular speed. Okay, we could determine the linear speed of this one if we are given the revolutions per minute, but what will be the formula and how to bring it out? Okay, let's try to bring out the solution. For the given problem, omega, Greek letter omega, actually represents angular speed that is under the study of kinematics. Kinematics is actually the movement of engine parts that rotates. That's why the movement as it goes, as it rotates, we term that one as angular speed. And for the given problem, angular speed is 115 revolutions per minute. And the diameter is 36 inches. So if we try to compute for the radius will be diameter over 2, or that will be 18 inches. Okay. I just now bring out the what we call this conversion, so when we go to the actual solution, okay, it's just a matter of direct substitution. The problem is asking what will be capital letter B, and capital letter B is actually the linear speed. At this point here, we'll try to run linearly in a straight line. How fast is it? What will be the speed? Okay. As it rotates, the speed is actually 115 revolutions per minute. That's fast, right? Per minute, it's 115. Supposing this point here will run linearly, what will be the speed? The problem is asking what will be the speed. Okay, let's try to bring out the solution. To bring out the solution, we shall convert first the so-called angular speed into radians per second. It's a mass, because what is given is actually revolutions per minute. So this is now actually a topic on angles, okay? Because the number one topic on the trigonometry that I presented here is actually angles. So this will now be an application problems for angles, okay? Omega, converting this to radians per second. 115 revolutions per 1 minute. Converting this to radians per second. Times, the operation is multiplication, 2 pi radians per 1 revolution. One complete revolution of a circle is 2 pi radians. Okay, so this is multiplied by 2 pi radians per revolution. And we shall convert this minute here to second. Okay, so we could visualize how fast is the point on the ring if it runs linearly or in a straight line. So this is, we know the relation of minutes and seconds, that is 1 minute. The equivalent is 60 seconds. This is the proper way on how to bring out the conversion, so we could visualize the cancellation. Okay, the operations are all multiplication, so we could cancel something on the numerator and so with the denominator. This revolution here cancel with this. Okay, the operation is multiplication. We are free to cancel. This minute here cancel with this. What remains? This radians here remains. Underneath is seconds. So after taking this what is conversion, the overall unit of the angular speed now will be radians per second. Taking the actual value, that will be 115 times 2 pi over 60. If we try to use our calculator, the angular speed represented by Greek letter omega, it is 12.042 radians per second. It's a mass that when we substitute omega, the unit should be radians per second. No, radians. It will not be revolutions or degrees, that's a different thing. As in the calculations, it's always radians. Okay, radians. Okay, let's try to compute for the linear speed. To compute for the linear speed, we need a formula. And this formula is actually the relation formula. Well, what relation? The relation of linear speed with respect to angular speed. Okay. The right hand side is a rotational motion, rotational. And the left hand side is a linear motion. Linear motion meaning it's a motion in a straight line. The right hand side is angular rotation. And the relation for this, that's why I place it here, formula, the relation. The relation of linear speed with respect to angular speed is linear speed is equal to omega times r. Since this is angular rotation, there should be radius or diameter. That's why there is an r over here. That is linear speed is equal to omega times r. Right? So by using this equation now, we could now compute for the linear speed, right? If this point here that is rotating runs linearly, what will be the speed? It will be omega is as per computation 12.042 radians per second times r. We converted this 36 inches to radius now, that will be 18 inches, right? So this is times 18 inches. This 1 foot per 12 inches, this is now a conversion factor. So originally the contents of omega times r is just these two here. And this factor here is just a conversion thing. So we must have to convert this, what you call this, inches to feet. So we will multiply this by 1 foot per 12 inches. Then try to make some cancellations. The operations are all multiplication. You can cancel something on the numerator and you can cancel something on the denominator. Right? The operation is multiplication. So these inches here cancel with this. Okay? What remains? Radians, okay, as it is. This is foot per second. So take the resulting unit of this now will be feet per second. But the angular speed should be radians. It will not be degrees, it will not be revolutions, it should be radians. Okay? So 12.042, am I still on camera? Times 18 times 1. 18 times 1 is just 18. All over 12. This over 12. The unit will be feet per second. And if we try to use our calculator, 12.042 over 12 is 1.0 something times 18. The value of the linear speed is, this will be the value. Okay? 18.06 feet per second. And if we try to take the graphical equivalent of this is the flywheel, rotating at 115 revolutions per minute. Okay, if we try to get the speed of this one, if it runs in a straight line, the speed will be 18.06 feet per second. Okay, that's it, guys. This is a good example of the problem on angular speed. Okay, good evening from Los Angeles. Angular speed, Professor David Reyes.